Welcome to BRR Media. Today I'm joined by Professors Andrew Easton and Nigel Dimmock. It's great to have you both with us today.
Hello.
Nice to be here.
So Nigel, can you tell us a bit more about how POLB2 was developed?
Yeah, I'd be glad to. POLB2 is an example of what we call a defective interfering virus. And they're naturally occurring, which is an important point in the context of this discussion. And the second thing is that they're non-infectious. In other words, they're not going to reproduce and produce more viruses. And they're defined by the fact that they've lost a big chunk of their genetic material. So that's the reason why they can't reproduce. But they occur naturally, and they are reproduced by the infectious virus, which is also present. Okay, so they're multiplied by the infectious virus, but they're rather ungrateful because they repay this kindness by actually inhibiting the replication of the infectious virus. So you can see where we're going with this. These are naturally occurring antivirals. And at the time when we started all this, many decades ago, the holy grail was to use these things as antivirals. Well, we started and we worked largely in animals. So did many other people, but we were the only people who managed to get these antivirals to work effectively. And they were, right from the beginning, extremely effective. We had two model systems. One was for a viral encephalitis, which was caused a very severe and fatal infection. And if you treated with these, what we call defective interfering viruses, those animals developed no disease at all. They were indistinguishable from ordinary non-infected mice. So it was spectacular. We didn't pursue that line of investigation for very long, but we went on to influenza virus, which was much more of a human problem and one which we wanted to try and do something about. Now, one of the problems of these precursors of POLB2 is that there are many, many different genomes, and one cannot work with this as an antiviral because you can't control it. There's no quality control. So the answer to this is to clone them so that you have a population which has a single sequence, and you have, by virtue of the sequence, a proper quality control. Well, for influenza, for a very long time, it was not possible to clone it. It was technically difficult, but eventually those difficulties were overcome. And at that point, joined by Andrew, we did that very thing and cloned a whole lot of defective interfering genomes from influenza virus, and then went back through the testing procedure. And we found POLB2, which was the best of the bunch at causing, at being able to protect the animals from infection. And we did a whole variety of tests, and it passed all of these in fine style. So we know a lot about POLB2. We know exactly what its genome is. We know the sequence. We know how many nucleotides they are. We know where it comes from. And that is what we're proposing to develop as an antiviral for use against not only influenza, but respiratory viruses in general.
So when did you discover that it could be a dual-purpose prophylactic and therapeutic candidate?
Okay, that was interesting from our scientific point of view, because the story was that these agents were limited to the virus from which they had originated. And amusingly, we did a control, being good scientists, and we put the POLB2 up against an entirely different virus, and lo and behold, it protected the mice from infection. Now we thought, oh, we screwed up here. We've got, it isn't a foreign virus, it's an influenza virus. But we went back and we verified it, and it was indeed a heterologous protection. And from that, we've used it against a number of different viruses, and we find that there are two different mechanisms, one for the homologous system and a different one for the heterologous system, which I expect Andrew will talk about later. Now, as to the prophylaxis and therapy, this was standard science. We infect animals, and then we either treat at intervals after infection, or we pre-treat. We treat prophylactically before we infect. And in this way, you can see the window of protection which exists prophylactically and therapeutically. So it's effective for both, and this gives it. So effectively, we now have a broad spectrum antiviral against respiratory viruses, which is capable of both prophylactic and therapeutic administration.
So turning to you, Andrew, how does RNA-based immunotherapy work, and what viruses could it be used for?
So the initial work, as you just heard, showed that the antiviral effect worked against a number of different viruses. The first work was done with influenza A, and then subsequently we showed that it was also effective with other viruses, quite distinct other viruses. This was back in around 2007. We obviously wanted to know how this worked. And so what we discovered was that if you did these experiments, these test experiments in animals that had a defective interferon system, they could not make or respond to interferon, then with the non-flu A viruses that we were testing, the animals were not protected. So that showed that there was obviously an induction of interferon generated by the RNA within POLB2. And we did show that it was RNA, not anything else within it. And what we now understand is that these defective interfering virus particles could enter cells, target cells, and they target specifically the cells that are going to become infected with an infectious virus or already are infected. And they induce those cells to make interferon inside the cell. So it's an internal mechanism to generate interferon, very like the natural process that goes on when you're infected, and quite different to the other approaches where you take in interferon in tablet form or sprays or whatever. So there's a very specific targeting and the production of an antiviral response within the cells. It tells the cells that they are being attacked by a virus, and they respond by a range of different mechanisms to eliminate the virus. And this targeting aspect is really critical, because it means that you only get a response locally where the POLB2 is located, which means that you don't get any of the side effects that you would normally see if you ingest in some form the interferon, so it's much safer. And the fact that it's targeted makes it very, very effective. It's very focused on exactly where the infections are located. And the other attraction is that it's instant. As soon as you administer this, you see the effect. There's no delay having to absorb or do anything else. It's an immediate effect. And with regard to the question of what viruses will this be effective against, well, in fact, all viruses are susceptible to interferon to a greater or lesser degree, but they are all susceptible. And so we predict, and subsequent tests have shown, that this treatment will be effective against essentially all major respiratory viruses that affect us.
So why is having a nasally administered antiviral so useful?
Well, the nasal administration is, firstly, you're delivering it to the site where the infection is likely to occur or has already occurred. So it's a localized delivery. It's a very simple and non-invasive. You're not sticking needles into people. You're not having to open them up in any way. And it's very cost effective. This is a type of administration that we're familiar with. It's used already in a number of different areas, including the administration of vaccines, for example, for influenza. And in principle, it's so simple that you don't need highly specialized facilities or trained staff to do it. It's something that appropriate staff will be familiar with and can easily administer this. So it's a simple, well understood, the techniques are available, and the equipment that you need is all out there and is used very commonly. So it's a highly attractive mechanism, but it has the benefit, it delivers the material precisely where it's required.
Thank you for your update today, and thank you very much both for joining us today.